So let's dive into some stuff about sets here. Let's start off with a problem. So if the size of A is 10, the cardinality, if set A has 10 elements in it, set B has 15 elements, and the union of A and B has 21 elements, what is the cardinality of the intersection of A and B? In other words, um, if A and B combined have a total of 21 elements in them, how many elements are in both A and B? This we can say as A or B, because they just have to be in one or the other or both. And this we can think of as A and, it's also called the intersection here. Well, I think the easiest way to do something like this is by a Venn diagram where we draw our sets A and B. And then we label. Notice there's four distinct regions. There's the part of A that's not in B. There's the part of A that's in B, here in the middle, the intersection. Part of B that's not in A, and the part out here in the universal set that's not in A or B. So we'd like to label things. The problem is the size of A is 10, but that includes both of these regions. These two numbers would add up to 10, and we don't know how. It could be 7 and 3, it could be 6 and 4, 2 and 8, 10 and 0. We don't know right off the bat. And similar to B, we know that these two regions here, the intersection and over here, add up to 15, but we don't know how that plays out. So there's a couple ways we could do this. One, we could just use some algebra. We could say, okay, well, there's X items there, Y items there, and Z items there, right? We have these three different regions. And if that's the case, well, we know that X plus Y equals 10. Why do we know that? Because the cardinality of A is 10. A has 10 elements, and there's two regions inside A, so those two regions, the size of those regions has to add up to 10. Similarly, we know B, Y plus Z, right here, equals 15. And we know that A union B, so A union B means it could be in any one of these three regions. So X plus Y plus Z equals 21. So this is what we have to go. Now it'd be a lot easier if we knew the size of the intersection of A and B, because then we could label that directly. If we knew that the A intersect B was 3, we could label this region in the middle 3, and we wouldn't even have to deal with working it out algebraically. But once we have this, we can think of it like, well, if we know Y and Z is 15, then what if we take this Y and Z together and replace them with 15? And this will tell us that X equals 6. We're solving for X. So let me put this in a different color just to highlight. Now we know that there are 6 elements in set A that are not in set B. And once we know that, we know there's a total of 10 in A, or whether we go back to the algebra here, if 6 plus y equals 10, well, that means y equals 4. And actually, that solved the problem here, but let's just double check and make sure everything else works out. Z then, we know that y plus z is 15. Our y was 4. So our z would be 11. So let's double check. Size of A is 10. Yep, 6 plus 4. Size of B is 15. Yep, 4 plus 11. And A union B, like being in any one of these parts, either one of these sets, is 21. Yeah, 6 plus 4 plus 11 gives us 21. So all that checks out. And then what's the size of the intersection? In other words, the elements that are in both A and B, well, that would be 4. There'd be 4 elements that are in both sets. All right, here we have a question. Create a Venn diagram where a certain region is shaded. And notice there's 3 sets listed out here, so I'm going to draw those sets. The thing about sets, it doesn't matter what their position is in terms of, I guess what I'm saying is you could have two on top, one on bottom. You can call this A, this B, and this C, or you could do A, B, C. As long as you label it appropriately, that'll be fine. Okay, what we really need to know is we need to know the intersection of A and B union C. Well, let's do this one by one. So let's do A in yellow. So notice that A has 4 different regions. So these are the 4 regions of A. And you may think, well, the example we just did, A only had 2 regions. Well, it depends how many sets you're dealing with here. The more sets you put in, the more possibilities there are of regions that you have to account for. And then we have B union C. Let's do that also in a light color, maybe in this one here. So B union C means you have to be in either B or C or both. And so this would be okay. This, all 4 in B. And there's also 2 in C that weren't in B. So that gives you a total of 6 regions that you shade here. So that's these here. But what we really want to know in this question is the intersection of these 2 shaded regions. In other words, it has to be shaded by both of the regions. Well, this was in both. Notice that it's in A, but it's also part of B union C. This right here was in A, and it's also in B union C, and over here. So really, everything is in there except the part of A that didn't overlap with B and C, which makes sense because in order to be in B union C, you have to be in one of those 2 sets, and this region over there would not be. This is only in A, not in B or C. So that 3 region shading shape there is the answer to our question. All right, next we're going to look at the Cartesian product. So let's, well, I guess we can just use the ones that are used in the homework. So let's say set A has the elements 0, 1, and 2. Set B is the elements 1 and 2. And set C has the elements 0 and 1. Now, we might just note, just to kind of remind ourselves of subsets and stuff, are any of these a subset of one of the other 2 sets? Well, A can't be a subset of B because 0 is not in B. A can't be a subset of C because 2 is not in C. We could write, however, that B is a subset of A because everything in B, each of the elements in B is in A. And in fact, we could also write that B is a proper subset of A because there's a leftover element in A. The element 0 is not in B, but it's in A. We could also write that C is a subset of A, and C is also a proper subset of A because 0 is in A, 1 is in A, and 2 is not in A. So that's just some review of subset. Now, Cartesian products, what this is, looks something like this. We're creating a new set based on an existing set that we had. And the way it works, you pick an element from the first one, so this would be C, an element from C, either a 0 or 1, and then an element from the second one, which would be A, either 0, 1, or 2, and you put them together in a pairing. So, the way that would look, let's do it systematically. So notice this first 0 is coming from C, the second one's coming from A. That 0 is coming from C, the 1's coming from A. And that 0 is coming from C, the 2 is coming from A. So those are the only 3 we can make with the 0 in C. And then we go through the same thing again using the 1 from C. Okay, and we get something like this. So the cross of C and A is the set of these 6 elements. And you might notice that what would the size of C times A be? Well, basically, for each element in C, you're going to go through all of the elements of A. And so it's going to be whatever the size of C is times, and by this I just mean literally times, multiplying 2 numbers, the size of A. Okay, so in this case, we'd have the size of C being 2, size of A being 3, and so the size of C cross A should be 6, and indeed, if we count the elements up here, we do see there are 6 elements. All right, we're going to jump to a really advanced question to end the video, where we have to prove that these two sets are equal. We're going to do this with a set membership table. And just like with propositions, it's very similar to a truth table. So this x is in A, x is in B, x is in C. We need one for each set that we're part of. And then we're going to go through this. Wow, got a little skinny there. Oh, very skinny there. That's a bit too skinny. You know what? Let me set this up and then unpause. Okay, now we need every combination of trues and falses for these 3 sets. This is another way of taking the Venn diagram with 3 sets and thinking about all the different 8 regions. Let me pause again while I do that. Okay, now that we got all that, we need to essentially create our little components here. So there's going to be A take away B, and then we'll take away C from that. And then over here, we're going to have A take away B, and we need to do B take away C. And then we'll end with A take away B, take away B, take away C. Okay. So A take away B, what we're looking is anything in A that's not in B. So it's got to be in A, first of all. If it's not in A, this one's not going to work out. And if it is in A, we just have to check if it's in B. If it's in B, we're only looking for the parts of A that aren't in B. So if it's in B, that's not going to work. But these other 2 are in A and not in B. Here, now we're looking at this column and taking away C. In other words, we have to be in this one to even qualify. So if we're not already in that, we might as well go ahead and mark that false. And if we are in A take away B, we just have to make sure we're not in C. So here, we are in C, so that's not going to work. And here, we are not in C, so that's the only one of the 8 that's in A take away B that's not in C. Now we have B take away C, so you've got to be in B. If you're not in B to start off with, this isn't going to work out, so I'm going to put false in those. And then the others, if I am in B, I just have to make sure that I'm not in C. So that one's not going to work. That one's in B, but it is in C, so that doesn't work. Only these 2 work here. And finally, A take away B, take away B, take away C. So I have to be true in this column, and I have to be false in this column. Let me go the opposite way this time. So I do see a true here, and it's not in B take away C, so this would be true. True, false here would be true also. Okay, the rest of these are false, which means these 2 are not equal because this column here does not fully equal this one because of right here. So these two statements